Now, if I were to look and say, what type of antenna am I going to build for, a satellite? All right, if I decide there's really two flavors of antenna types, you could do a slot type of antenna, very popular. Those are for high power type of applications. But if we're looking at satellites that are near Earth, we probably don't want it to be very heavy. So depending on your application and the design needs, will dictate what type of physical geometry we're going to use. Of course, electrically, we also have constraints to in that as well. Okay. In the day of internet and Google, and I could get any information I want if I decided to do an internet search. So I said, okay, what did SpaceX send up in their Starlink antenna? So I went online, watched the video. Here's the Starlink, and someone actually did opened up the Starlink transmit from on the Earth side. And if you look at it, they tore it apart, and you could see they're patch antennas. And we could see little indentations and notches. Probably, if I were to look at it even closer, I could see some, indentations for the different polarization. It looks like it's on some flexible material, but it is, glued to some structure here. And maybe there may be an air cavity in here. And then you could see some, if you really look deep, and I did, zoom in, I could see some chips in there. So there's, electronics on there. So with that, I said, all right, recently, April 14th, 2022, satellites were successfully launched at 340 miles, 550 kilometers, LEO's orbit, standard transmit receive frequencies at 10 and 14 gigs. And let me take a look at the inner patch antenna and make sure that it's circularly polarized. Okay, so what would I do? Well, in the Ansys HFSS electromagnetic simulation tools, we also refer to it as AEDT, the Ansys Electronics Desktop, but the solver is called HFSS, High Frequency Simulation Tool. So we have a wizard, what we call the Ansys Antenna Toolkit. And perhaps you use Dr. Balanis's textbook in school, and there are equations for the design of several different antenna types. And we can look at a patch antenna, different varieties of patch antennas as well. We can also look at slot type of antennas. And you can see we have many different antenna types that we can build for you to give you an already made geometry. So I'm going to look at the patch antenna. You can see it says, or hopefully this button says synthesize. So according to the equations, I set the frequency. 10 is fine, right? Give it a substrate and boundary conditions just to set it up. It's some information of where we, how to design the antenna type. And I hit finish. And what will I come up with? I'll have a HFSS model. Now, because Ansys wants to encourage students, to use our tools, and also a way to disseminate knowledge and use modes, right? Because the industry uses HFSS, we want our students to learn the tools. We do have a free Ansys Electronics Desktop, a student version. Yes, it's limited. Yes, it mimics our fully purchased tool, but again with some limitations there. Okay, we're going to go over again electrical design, we'll go over the Multipaction, and we'll make sure that it's conformal. Okay, here's the website for the free academic tool. All we need is a email address, and when I hit synthesize shot of the HFSS user interface, I come up with a model, right? So if I go back here, here's the picture or the image of what I'm going to design. And you can see there's some parameters there. Well, I get the model. I get what I decided to use as my board material and some metal materials. I get the excitation, the things that we need to start and initiate an HFSS model. What's going to excite it? What is the source? 4 patches, 4 types of excitations, an analysis setup. The analysis setup with 10 gigahertz, okay? And result plots, return loss, input impedance, our gain plot, and our port Z0 plot. So if I decided that, the manufacturer says to me the board is at a different height because there's a tolerance there, yes, these are parameters that I can then change. Maybe I want to change, I wanted a start model. And or perhaps my assignment was, what's going to happen, or how does the antenna characteristics change with these notches? What are these notches for? Again, you can change those parameters and see what the changes are in your gain pattern. Or perhaps it's changing frequency. It's for you to know, right? So we go ahead and we synthesized an antenna model or structure. Make sure that electrically it's at the frequency we want. We take a look at its radiation pattern and its input impedance. Perhaps your job is not to design the antenna, and you need to design the feed section. So on the input side, you need to know what the impedances are. And I said that we're going to look at a space-based application. So there is a phenomenon that is only associated with space-related geometries or space-related experiments, and it's multipaction. So what the heck is a multipaction? Well, it is an electron phenomenon. It's not something that we're going to probably look at, on the undergraduate level, but it's a consideration that you need to look at. What is happening on the electron level? What happens when you're in a vacuum? That's when multipaction occurs. Space, a vacuum. And when there's high power, when there's enough energy, there's enough RF signal transmit power that's causing the electrons to duplicate or to grow or to increase. We do have at Ansys, again, not only do we have a free student version, you can even try out Multipaction and understand more through our Ansys Innovation Courses. Again, it's a free course, and we will teach you about Multipaction, what it is, fully describe it, okay? We'll have what it is fundamentally. When I said electrons, what causes it, okay? Let me tell you, what really causes multipaction is the materials that you're using your element. Not only are we concerned with the electrical aspects of it, but it has to be manufactured. It has to be created. What materials are using? And those materials have characteristics. Not only, we may have looked at the board and say, hey, dimensionally, I just said height. But not only are we looking at the permittivity, the relative permittivity of the dielectric, looking at, yes, the surface. Is it flat? Is it going to excite an electron? We're going to look at the electrons that are in the metals, look at how the electrons are going to move, what we call the secondary emissions. That is a key word when you're talking about multipaction, the SEY values. What is the probability that an electron will hit a surface, whether it's dielectric or metal, and then from itself create another electron? Similar to laser diodes, avalanche, the phenomenon of avalanche diodes and electrons. And so that's what you can learn from this Ansys Innovation course. And then we'll show you how to set it up and to analyze it. So what will we see as a result? Well, for that patch antenna, and I only created a view of one of them. Okay, let me play this one here. Now these little red dots, and hopefully it's you can see it in your presentation screen. These little the blue dots are supposed to mimic electrons. Where are the electrons in the vacuum space? So the makeup of this particular patch had a air-filled, a vacuum-filled connector. And so where are the electrons? The electrons, yes, can be in the dielectric, but we need a vacuum because it's space. So I created an air-filled. This is an air-filled coax, and this is where the electrons are. So as the electrons, and they're moving in all directions. It's not just X, Y, and Z. So they may be accelerated through the field here. Perhaps they're emanating from that inner pin, hits the sidewall of the connector and bounces back. And perhaps just at the time of resonance of the RF signal and the electron velocity, it may produce another electron, maybe 2, 3, or 4. And so that's what this graph is. So if I started at some time frame, I have how many electron particles? Maybe I have 2,000. It looks like I may have started with 1,000. And then according with time, this red curve was 1,000 watts. If I had 1,000 watts in here, am I going to initiate a multipaction? No. Well, if I had 2,000 watts, will I initiate one? Yeah, look at, the number of particles have more than doubled. So this is a way of saying, hey, please be careful that this part cannot handle more than 1,000 watts. This I did a step size on this. We also have an auto solve, so it'll give you the exact power level where multipaction, where the secondary emissions, where I will see this become more blue. Okay, so that's what multipaction is. It's the probability that an electron will reproduce itself and create another electron in the vacuum. And why is this important? Power handling. Well, I hope I have enough signal power in to send a signal back down to Earth, right? Maybe perhaps it's something to say, hey, please be careful for the connector. Maybe the connector is my most probable part that will be a power handling issue. And we can do this in simulation. We don't want to test it out during mission, right? Because that's a lot of money spent on creating it, but we can make it the entire mission. And that's why we're starting off with the antenna. We could do multipaction on an entire system, but here is just for this one patch antenna. So we say, okay, maybe the statement of work said 1,000 watts. Okay, easy. If it had said 2,000 watts, yes, we would create an issue and we'll have to make modifications to this part of the design. You may or may not see that I had selected in the setup for multipaction the entire vacuum space. Vacuum space was not only on the inside of the connector, but in the regions inside the cavity that's enclosed within the entire antenna element. So there are electrons that are in the space outside of the connector. Again, you will be able to see that in your simulation. Okay, so now that we're happy with the electrical design, we're happy with the multipaction response, now I want a more efficient way of creating the array. And as you saw, when I tried to reverse engineer the Starlink antenna, there are hundreds of elements. I am not going to go here and say copy, paste, and put it in the exact number of elements to create this patch. Again, that would just, yes, I can automate it. And we do have automation tools. We do have a PyAEDT script that we can write to create it. But we already have that within Ansys. I can create an element, a 3D component element, an HFSS submodel of this unit cell. And then I have a finite array wizard that says, oh, I want this to be replicated a number of times in a row, and I want this many columns. So I can automatically create it. And you can say, yes, oh, so what's that going to do? Well, when we create a 3D component and we use the finite array wizard, not only are we efficiently creating the model geometry, we are also going to efficiently simulate that, because we can reuse the mesh of this component as we created the array. We'll simulate the whole thing, but we have a start mesh. We know from this unit mesh where we started, and we have the idea of reusing that mesh. So why does that matter? We don't have to start all over and remeshing every single element in that array and times that by 100. Reason why you may want to use a 3D component. Again, efficiency. We're always looking for time savings and resource efficiency. So I had mentioned the idea of a component array. Oops. How do I get rid of this? Well, hopefully you could see it. I don't know how to get rid of that little blip up top. Oh, it goes away automatically. Okay, good enough. All right. So I use 3D component. And you can see I kept the same name as what I came out of the antenna toolkit, the sequential rotated patch antenna. What's also nice is, like I said before, you may not be the major antenna designer, and you just need that element because you got to create that feed section. That's why I put that input impedance as one of the results. And you may need to create that feed, and you have to include the parasitics. But you're the manufacturer of the antenna, and you don't want the feed engineers to know what your design is. So you can encrypt those components, and you could even password protect it as well as encrypt that 3D component. And when you come in with a 3D component, you get the model geometry. Yes, you can hide it and use it just as a black box, but you could see that with a 3D component, I could bring it into the model. I don't have to recreate it or copy projects. I bring it in as a component. It looks like a circuit model, or circuit element. But all the materials come in, and the setup comes in. So like I said, it's like a small mini HFSS model that I could use repetitively. Use the finite array wizard to create this array. And again, I could come up and look at, the S parameter plot, the return loss, is it still about 10? Yes, I could look. Yes, there's a big change in the array when I look at the radiation pattern, and I could look at the 3D gain plot as well. Starlink, as you saw, was flat, and it looked like, because they had some of those supports, you could see like a cavity kind of honeycomb type of structure. But nothing stopped me in taking that array and placing it on some sort of curved surface. Okay, maybe I'm not using it for on a flat structure, and maybe I'm not placing it in some circular pattern with a flat, hard based board. Perhaps I'm putting it just maybe on a parabolic dish antenna, and it is a curved surface, but then I want it to be flush. Well, I can go and I'm still using my Ansys electronic desktop, my AEDT, but I'm going to push into a different solver. Instead of my HFSS solver, I'm going to use the SBR plus solver, our shooting bouncing ray solver. Just another solver type, We're going into different dynamics and different scales, and we want to make sure that we include, all of these dimensionalities in our solve techniques. And so I'm going to use my SBR plus solver to put this array on this curved surface. Again, all coupled in the same user interface. Makes it very easy. Okay. And now, whether I want it on that curved surface or not, and I want to go and mount it on something, again, if I put it on a curved surface, I do have changes to the radiation pattern from the array to this curved surface. Notice that I have extra back lobes here. But now I want to port it and put it on something larger like the satellite. Well, the way we export that data from the far field is in that in the HFSS project, I can export fields, and I export those fields in a format, in a far field data format that we use within Ansys. It's a text file. And what we want to do is kind of port it to a different tool that I use within Ansys, which is our STK tool. because I'm going to do some more of a situation awareness. You know, can I really communicate from that satellite, the Starlink, which I'm looking at, to perhaps Ansys headquarters? Well, I go into my STK tool, and yes, we can have visuals, and we can take a look at Ansys. This was from Bing Maps, okay, and this is our headquarters in Canonsburg, Pennsylvania, in North America, in the U.S. And I want to look at one of the Starlink satellites and mount that antenna that I used, that I designed on the satellite, and I want to make sure that I can connect to headquarters here. If I look out more, and if I looked, and as you saw, I Googled, I did an internet search on Starlink, and they say, oh, they used a circular orbit. They use a LEO's orbit. Okay, here's a circular orbit around the Earth, and here's Ansys. Within that STK tool, we have a database. It does link to our national database, and I could pull out several different Starlinks. We have hundreds, right? We have hundreds of satellites out there. And I routes, but I really don't cross. Location-wise, I really don't get close to Ansys. And I look in a little bit deeper. That's because we don't have Starlink coverage in the Canonsburg area on the east coast of the U.S. There's a lot of Starlinks that have coverage on the west coast, but the east coast is just not there yet. So, okay, well, I guess I got to have a different type of satellite. I already designed my element, so what would I need to do? Well, another type of orbit that is very popular for satellite communication is the Moynihan orbit. Okay, so let me create a satellite in the Moynihan orbit instead of the circular orbit. What's going to happen? Okay, I'll set up my STK tool. I'm going to use the Moynihan type of orbit. I said above, when I was looking on the internet, they were launching for LEOs at 550 kilometers. I'm going to see what happens. So I set it up. Again, library databases just for coverage. Am I going to connect? Am I going to have access to Ansys? Well, two different orbits. This pink orbit is a circular orbit that I thought that I was going to use for a satellite for Starlink. And this is the Moynihan orbit. Now, I'm going to play this video just a little bit, okay? And you'll see the dots here as the satellites are, propagating around the Earth. Again, circular and Moynihan. And down here is just a snapshot. This is a static snapshot. I didn't have time to capture the entire video, but you can see the top orange bar here is the time. Let me just stop this for 1 second. The time that the Moynihan orbit has connection to my target, which is Ansys headquarters. Let me just roll this back a bit. And in this video here, let me just go around. You can tell that it's a little bit of a lag time, but this blue line here says, oh, I'm actually in this orange area. I actually have a access to Ansys headquarters. Down in this next row is the circular orbit. It's the pink orbit. Do I have access to the target? I only have the access in comparison to the Moynihan orbit a small amount of time. We can give you those times, okay? Again, based on some measured data that's taken. And I could use a 24-hour period. Here's just an access report. I don't expect you to read all the details, but at most, if I were to look at the circular time in a 24-hour period, I will only have total duration here says about 90, less than, about 10 minutes. This is durations is in minutes, about 10 minutes of duration time here for connecting to Canonsburg. It makes sense because there's no Starlinks up there. Okay, so maybe for the Moynihan, what happens here? I have 994 minutes total. So again, I have more duration times, and I could look at it, just visually here on this timeline on the axis. So let me continue with this here. Hopefully you'll just see as it goes around, you'll see a blue line during the access time, and you'll see a pink line that goes to the target here where this teardrop, this yellow teardrop is. Okay, so let me go ahead and show you. So now if I just expanded it, just looking down, what I want to show is here's the satellite. Here is the Moynihan, and you could see this blue line is connected to Ansys headquarters. Now this here is a coverage map. It's like, if I'm up here, what's my coverage area? I can set that. I want to make sure that I'm looking again at situational awareness. Am I looking, what's the radius of that sphere that I'm looking at? This could be very targeted and focused, or it could be very wide in range. And this will give you a visual of what area that satellite is able to cover. But now the idea is, I took that antenna element, I created the array, I made sure that, electrically and for Multipaction, that it met my specs. And now I want to take that far field data, I exported the FFD plot, now I want to put it onto that satellite. So within STK, you can insert that very specific antenna design. And as you can see here, the option is the Ansys FFD format. So I want to take the results of my simulation of that antenna array and place it on the satellite. So I could go through here, put it on there, and see if indeed I can do that. And so this is all integrated into one because I use the Ansys workflow. So I wanted to look at the element. I wanted to look at the electrical design characteristics. Again, I used the Ansys toolkit with that. I use our Multipaction feature to see how much power I can use on that antenna element in order, in my scenario, whatever the customer wanted. I used our 3D component feature to help reduce or make the simulation more efficient. Again, reduction, what that means to you as the customer is, simulation person, less simulation time. I'm not sitting around for, days waiting for a result. And then I placed that in an array. I put it on some sort of platform, which was the satellite. I did a situational awareness. I had a satellite. I knew it doesn't have to be a satellite. Okay. I could have been, an airplane. Before the Ukraine situation, in the U.S., we had the 5G rollout issues with the airport. So you may have seen, there was a lot of talk in North America about when the plane is coming into the airport, it may be on autopilot. And those electronics, and some of them were a little bit dated, the electronics of the 5G and the harmonics and the frequency of the altimeter, and that altimeter was used to see what the distance of the plane as it lands to the ground, and it has all these other radar controls to make sure that you're not going to bounce off of the tarmac and you're just going to land nice and smoothly. Well, there was a frequency range for future, and I'm going to say for future 5G rollout, that it may interfere. In short, there were lots of simulations done, different scenarios, but in short, yes, there were some specific cases where the frequency of the altimeters and the frequency of the 5G band may overlap, okay? And it may be worse, if other factors like propagation, if there was, if there were rain and, wasn't clean air, that you may have a reduced signal to noise. And so maybe not only was there power and frequency overlaps, but it was for future 5G. So this is another reason why you can use HFSS and STK together. So anyway, so we used all those. We can use a variety of different situations to test out the antenna, add different parts. This was very simple. I'm not limited to just one antenna. I could put other excitations in there or put other geometries in there as well. So with that, hopefully, I said what we're going to do is go and design a single element, We used the ATK, the antenna toolkit, to design it. I created the array using 3D components and the finite array element. I mounted it on the satellite. I used STK and used situational awareness, and I went from the LEOS orbit down to Ansys headquarters and showed you Multipaction. And we did see a course that we do offer at Ansys and a free download.